My name is Dan O'Mara. I'm here to talk to you about Geo2Flow. Geo2Flow is a plugin that goes after compartments, saturations, and permeabilities. So we're into identifying flow compartments in the reservoir, calculating 3D saturations that honor your logs, and estimating perms constrained by saturations. I want to start out with a metaphor. I was faced with a situation 3 years ago where I had, on the one case, a homogeneous situation, on the other case, a heterogeneous. Anybody recognize what this stuff is? What?
It's a cardiogram.
Yeah, it's an electrocardiogram. So if you were at a certain age, you would get that, you know? So some of the folks in front here are less likely to get it. So I had a problem called atrial fibrillation. Most people in this room, their heart goes bump, bump, bump. Mine would go bump, ba-dum, bump, bump, bump. And so that's a problem. And so here are the solutions that my doctor offered me. Okay, I can take pills to solve the problem and deal with the side effects of the pills. Or I can undergo a high-tech catheter ablation to actually burn sources of electrical activity in my heart. Okay, so it's an outright cure. It's a high-tech cure. Okay, now before you understand what went into the decision making, I have to tell you the number one side effect of the pills. The number one side effect of the pills is irregular heartbeats. Okay, so that's a bit of a problem because that's the problem you're trying to solve. So maybe instead of going bump, ba-dum, bump, maybe you go ba-da-da-dum, bump. You know, so you just get a different kind of irregular beat. So when it comes to saturations, perms, and compartments in the industry, we've been taking a lot of pills rather than the cure. Okay, so there's a high-tech cure here, and it doesn't have the side effect of the pills. The side effects are unidentified compartments in your reservoir, saturations that don't match the logs, and unrealistic permeabilities that are not coupled to the saturations. So let's see, start with a little quiz here. I've got 10 log measurements that penetrate a Petrel cell. Okay, here are the 10 measurements. 5 of them have a water saturation of 1. 5 have a water saturation of 0.2. We're up above the free water elevation. Okay, so the question is, what is the average saturation? Okay, and it's multiple choice. Geologist choice is usually number 4. So anybody?
You cannot have 100% on top of the point.
I guess you could. Oh, you can't. Oh, of course you can. Look at the logs. What it means is if you actually start to think of it, okay, if the porosity is 0, okay, then you can easily have 100% water saturation. And so here, if I start to put the porosity in, you start thinking, well, this is a little bit related to pore volume. So it turns out the average saturation is 0.2 because all of the pore volume is down here, okay? So, but if you go into Petrel's upscaler, okay, the default is to get 0.6, which is what most people would do. So when I tell you, the reason I go through this is when I say that one of the things Geo2Flow does is it honors the saturation logs, one has to understand what it means to honor anything, right? Because well, what is it that we're honoring? We're not going to honor 0.6. Okay, we're going to honor the proper pore volume weighted saturation. Engineers a lot of times don't get that because they understand you should be pore volume weighting. But when I first mentioned it to Kent Thomas, somebody retired from ConocoPhillips a number of years ago, he didn't believe me. Okay, and so I had to take him into the geological models to show exactly what they do. Okay, so the proper way to average saturations is by pore volume weighting. You'd think that'd be straightforward for an engineer. Okay, so let's look at some models. So we have a nice tool in Geo2Flow, part of the Geo2Flow toolbox, and it allows you to cross-plot your 3D property, saturation, versus the upscaled saturation, the pore volume weighted upscaled saturation. So we can go in and use this module to do like peer reviews. So let's see how we're doing. Okay, here's a model. It's a real model. So what we got here is we got the saturation coming out of the logs that has been properly pore volume weighted versus the saturation in 3D. Okay, this is what we get with GEO2FLOW. Okay, so we pay a lot of money for the logs. Why don't we honor them? Okay, and a funny thing, you know, in the Petrel project that's used for training, somebody had it up earlier, it turns out there aren't any saturation logs in that project.
I had to make them up.
And so the number one rule of saturation modeling is actually you need the logs in order to honor them. Okay, and so GEO2FLOW in the toolbox, we have this nice little tool here where if people say, oh, of course we honor the logs. Yes, we honor the logs, yes. I go, oh, really? Okay, well, just let's try it out and see if we're honoring the logs. And I would say 9 times out of 10, we get something like this. Now, if you're using net to gross, you know, and you've got a nice picture, you've got a beautiful picture, and the question is it right? You know, are we honoring the logs for this picture? So let's look if we have the 10 log measurements, okay, but now I've got porosity that isn't 0. Okay, the average saturation would be 0.2 pore volume weighted, but if I assign a net to gross cutoff, okay, the average net saturation would be 0.2, okay, if I cut this off. Okay, so the proper way to average here, if you've got net to gross, is net to gross, net pore volume weighting, okay, net pore volume. And so here we go. Here's a model where we're not using net to gross, and here's one where we are. Okay, net to gross is in the model, okay, but it's not reflected in what's out there in the 3D variables. Okay, so that's a mess. Okay, in terms of GEO2FLOW, what do we do besides saturation logs? The process goes like this. You start with a Petrel model that has porosity and water saturation logs. Most models do. You start as early as a rudimentary geological model. If you're early in the process, you get fluid densities, you get a 3D porosity, and then you use GEO2FLOW to get 3D oil, water, gas saturations and volumes, all that honor the well data. Okay, honor it in the way that is proper. Okay, so and then if you're using net to gross and net porosity, we're going to give you that. We're going to distinguish between a horizontal perm and a vertical perm. If you're using poro-perm correlations from the laboratory and putting them in your Petrel model, you do an excellent job of underestimating the perm that the engineer needs for the well test. Okay, so fluid contacts, reservoir compartments, rock types that are tied to J functions. If you've got a perm log, great, but we're going to improve it because perm has to be constrained by saturation. If I'm up above an oil-water contact, like you saw earlier, and I have a water saturation that's near 1, that's low permeability rock, okay, and that has to be honored. And then if you want to take it back into ArcGMNN and redo your petrophysics, we can do that. If you have more data, then it's just going to constrain the process. So if you have lab cap curves, poro-perm data, a detailed geological model, perm logs, and so forth, you're just going to get better answers. Okay, this is patented technology. There's 2 broad patents covering the methodology that's discussed here. Okay, we've used it in data poor or data rich environments. More data, just better constrained answers. Okay, we use it with oil and gas reservoirs with up to 1,200 wells in one field. We use it with clastics, and remarkably, some people think you can't use this in carbonates. That's just funny, because in carbonates, you need everything you can bring to the table. Okay, and so why people throw good laboratory information out the window with carbonates, I haven't a clue as to why that happens. And if you've done spreadsheets, like Jeff mentioned, folks doing spreadsheets, then that's great because you understand the physics, but we've connected it all to the Petrel model. Okay, we've done a lot of projects, and this is just a smattering where you have so many wells, a couple. We've done a 1-well project, the zones, quite a variety. On faults, we've done up to 1,000 faults. Cap pressure, usually you have it. Poro-perm, usually. Facies, for all the talk in the industry about facies, a lot of models don't have facies in it. And pressure, yes and no, okay? So one that I really love, though, is this field here, 183 wells that had 1 zone, no faults, and absolutely no data. okay, we could show from a geotoflow analysis that we had about 5 compartments in this field that they're about to polymer flood. Okay, so it's like you wouldn't want to not know about those compartments. To give you an idea of why we use J functions, here's some cap pressure data expressed on a cap pressure plot for a deep Gulf of Mexico field. Once you start to look at J functions, log-derived J functions, here's the data from the laboratory, these curves. It starts to orient your thinking, and you start to think about what are the possibilities for my reservoir. One possibility is I've got the wrong free water elevation. I need to modify the perm. Or maybe I'm going to just draw in a new J function here that I haven't seen on my core data. So it gets you thinking about how to change your model. Here's a model, highly faulted model, 350 faults in this model. Beautiful data set. We see nice cap curves. We see a very narrow range of J functions. So here's the log-derived J function data. How many J functions would you put through this data? There's 500,000 data points on that plot. It's one heck of a mess. That would not stop an engineer from doing something like this to go to Eclipse. And that leads, all of that scatter leads directly to errors in volumes, directly to errors in reserves. Now, here's what happens when you tie it to a Petrel model. Here's exactly the same data, but this is 10 wells in one zone, 26 wells in exactly the same zone, different fault block, 5 wells in a different zone, in the same zone, but a different fault block. Most of the scatter here and here has gone. Why? Because we've sorted out the different reference elevations, the different free water elevations. We see compartmentalization. Okay, so let's see. Here's, for instance, a field in Ecuador where we had 16 fault blocks that were seen from seismic, 6 compartments seen by geotoflow analysis. I'm trying to give you, in 20 minutes, I can only give you kind of a broad brush. I'm not going to go into the detail here, but I want to kind of give you some ideas of things to be thinking about with saturations, compartments, and perms. Okay, with pressure data alone, a lot of times if you've got pressure data, green is oil pressure, blue is water pressure, you can see we have a beautiful fit on the water, but the oil's not quite fitting. So if we use that water fit to calculate the water pressure at every green data point and subtract the water pressure from the oil pressure, we get the capillary pressure. And if we plot up the capillary pressure, we start to see patterns like this, which might suggest at least 3, 4, 5 compartments, depending upon what we're seeing in the Petrel model, because after all, we're going to be looking at this in a geological context. Here's some deep Gulf of Mexico data. You can see 3 different wells here. The green seems to be above the blue and the red. And indeed, it looks like you can match the data from the laboratory better with putting a different free water elevation on one of those wells. That's very important if you're paying, $250 million a well, then you would want to know if you've got compartmentalization going on here. Okay, here's where we go in with an original J function in a particular zone. This is a narrow area of the reservoir. We allow some errors in perm and Archie exponents, say, and we can get all the data onto a limited number of J functions, but then you see that the original permeability has to be modified because the saturation's telling us something. You know, it's very funny how we model in the industry. We start with facies and porosity. We go to perm. Wait a minute, perm. We're very unsure of perm. Why are we going perm next? Because after that, maybe we'll go to saturation. Well, wait a minute. What about this thing that we're so unsure about, perm? Okay, we want to wrap the perm modeling in with the saturation modeling. Okay. So let's see, here's a bunch of wells. We put it on some J functions, found the different free water elevations, and then we actually get J functions that represent this data with a reasonable amount of noise in the permeability, but that perm has now been constrained by saturations. A common assumption, if you get log-derived J functions or J functions from the laboratory, is that you can use the same J function that you got on a core this big in something about as big as 5 stories in this building. Going into the model. That is a leap of faith. GeoTOFLOW tests those leaps of faith. Here's what happens when we go into a Petrel cell that has a fair bit of heterogeneities in it. We don't get the same J functions. They degrade. Okay? The assumption is they don't. In GeoTOFLOW, we test it. We want to make sure that it doesn't. If it does, we're going to deal with it. Okay? But most people don't even recognize that this is happening because they get data from the lab or from the logs and don't assume that upscaling plays a role. Carbonates, let's see, permeability. There's a lot of silliness in saturation modeling in the industry. One of them is called saturation height functions that don't depend upon perm, just depend upon porosity. So therefore, when you have a porosity of 0.2 above an oil-water contact or a free water elevation, people have a hard time understanding why the water saturation can vary between 0.2 and 0.8. Okay, the reason is because at a porosity of 0.2, you might have a lot of noise, 2 or 3 decades worth of noise and permeability. Permeability is the key. Now to tie that back, okay, if saturation and perms are so intimately related, then we're going to learn something about the perm from the saturation. Another thing that we do in GeoDaFlow, we see more and more of this stuff, is bimodal curves. These also have bimodal relative perm curves, as well as bimodal J functions or capillary pressure curves. We handle that kind of stuff. We spit out from J functions relative perms, which are usually difficult for the engineer to get a hold of good data. Okay, we also see a lot of models in Petrel where we have problems like this. See the blue data? Okay, what's going on here? That's at a point where we try to encourage people to go talk to the petrophysicist. Check out your Petrel models. There's usually a bunch of porosity logs, perm logs, facies logs, one water saturation log. Most models have one water saturation log. The training model of Petrel doesn't have any, okay, but one saturation log. That's because the petrophysicist gets it right to 4-digit accuracy. There's absolutely no error in the saturation log, okay? I'm being facetious, right? So there's plenty of error in it, and it should be wrapped into the whole uncertainty loop. Why is that the case, okay, that we get one saturation log? Number one question petrophysicists asked about GeoDaFlow, can I run it just from LAS files? I don't want to use Petrel. I'm a petrophysicist after all. Okay? So what we're going to try and do is we're going to try and bring those petrophysicists into this process, because if nothing else, it's in their best interest. Because if they say, here are my multiple realizations of the logs, and it makes this kind of effect on the volumes in the reservoir, they may have easier time getting funding from their management, right? Because they're now tied into not just the log interpretation, but to volumes. Okay, lots of documentation behind the scenes here in GeoDaFlow. There's like basically a book online. Okay, who owns the GeoDaFlow process? Some people say a geologist because it connects to Petrel. We look at flow compartments, we look at faults and facies guiding distributions. Some say petrophysics because we do well log interpretation, special core analysis, rock physics. Some reservoir engineers, we connect to Eclipse, we do PVT, MDT, reserves, upscaling, and history matching. But what we've designed it for is the acid team. We actually have champions in the 3 different disciplines at different companies. GeoDaFlow is a Rorschach test, an ink blot test. You know what that is? You look at the ink blots, what do you see? Okay, hold it up. If you see GeoDaFlow, petrophysics, geology, engineering, tells me more about the company than it does the product, okay? So we had one chief petrophysicist who was in a course that I taught who said, if we do it right, we'll involve all 3 disciplines because this is truly interdisciplinary software. Here's a capture out of Petrel. Let's see, if you're using poro-perm correlations from core, okay, they underpredict the well test perm. In GeoDaFlow, we calculate a well test perm that is different than just getting correlations from the core data. And there's a properly upscaled horizontal or well test perm. And you can see just from the colors that it's quite different. This is a reason that geologists get bad reputations with engineers, because they hand off to them perms that they can't well test match. So talk about history matching. Okay, compartments. Reservoirs are compartmentalized. In fact, they're oftentimes more compartmentalized than we think. And you have to ask yourself, why are you overlooking the compartments? They're out there, okay? So you need to be considering compartments. Okay, we have a very nice workflow here where we do all this work to get the saturations, perms correct, and then we'll take it right into Eclipse. So with the RE component, here for instance you see GeoDaFlow properties here that have been filled out automatically when you do a GeoDaFlow run for Eclipse 100 or 300. These are the grid properties, the 3D data. Here are the rock physics and fluid properties we actually put out there for the different rock types or J facies. We put out relative perm curves. We put out capillary pressure curves, we put out the fluid properties and the equilibrium regions. We're all ready to do a SWOT, a NIT. Here, for instance, is all of your properties out here, your different fluid properties and the like in the output tree. And here's, for instance, a spreadsheet showing the capillary pressure data that gets put out by GeoToFlow. So a nice, smooth workflow. Geo, Petrel, into, flow, Eclipse, okay, all together. Okay, if you've got a lot of rock properties, you know, engineers, when I ask them how many cap curves do you use, one probably, a couple maybe. So, but here we have something like 18 or 20 or something like that. We have multiple rock types, and we can handle that kind of stuff. It's just more data that you feed to Eclipse, more data on the tree, but it's all done automatically for you behind the scenes. So, so it's written using the sat-num index of Eclipse, the different rock types. So when it comes to saturation modeling, when it comes to reserves, when it comes to perms and compartments, okay, you have to ask yourself, why would you want to keep taking the pills and dealing with the side effects? Okay, because that's typically what people do. And so you have to ask yourself, if there's a best-in-class methodology out there for something as important as reserves and volumes, why aren't you using it? Okay, and so we identify compartments, we calculate saturations that are on the logs, we estimate perms that are constrained by saturations, and we run with Petrel in the ocean ecosystem. So when it comes to reserves, why would you use anything less than best in class? Okay, so that's kind of an introduction to the GeoToFlow plugin.